Hi, good evening. Today's class we are going to see about radioactivity as I have written here. We'll go through the basics in this video. Probably in a following video we'll see it in detail about what are the types of questions that could come, how to solve it and so on. So here I'm going to just go through what these key terms stand for and how to use it in an explanation or just an overview understanding of this terms. We'll see it. All right. Now, what is radioactivity? Now, most of you who have already learned might be familiar, but then when does it occur? Why does it occur, etc. Now, when you look at the atoms who are or which give out radiations, if you just do an analysis, you will notice that majority of the atoms which give out radiations will have very high atomic number. Right? Those high atomic numbers, certain elements are unstable. When they are unstable, they tend to give out some of the particles or some of its mass or charge, etc. They give out to reach to a stable state. All right. So a heavy, unstable element, it gives out some radiations or it just emits some of its particles, and then it reaches to a state where it is going to be a stable element. All right. So these radiations that are given by this atom are like, they have different properties. Those are classified based on the properties. There are three types of radiations which are given out by these unstable isotopes. They are alpha, beta and gamma. So how do you write the definition of radioactivity? It is the radiations given out by an unstable isotope, isotope, to form a stable state, and you can write about the characteristics of these three radiations. Now, alpha is written by the symbol beta and gamma. Right? As I said, these three have got different difference in terms of their properties, characteristics, etc. We'll see that. Right? Now, alpha and beta are charged particles. Okay. Now, gamma, we say it is uncharged or neutral, and it's a radiation. So what's the difference between that particle and radiation? When it is particle, it has got mass, right? But radiation, it does not have any mass. It's just an electromagnetic radiation. So these two can be termed as particles, and this will be termed as radiation. That's one main difference, right? Now, particle, and I said these two are charged particles. So both of them possess a certain amount of charge. Now, alpha possesses +2 charge and beta possesses -1 charge. All right. So I have covered here this. So we have spoken the three particles. Actually, there is a table in your textbook. I'll try to insert in this video. Majority of the physics textbooks will have that table where it is differentiated in terms of charge, mass, etc. So here I'm just giving you an understanding what it stands for. So for you to retain the information, please go to that table and by heart it. You must know about these properties. All right. So alpha is +2 charge and beta is -2 charge, and gamma does not have any charge at all. It's a radiation. Now, when they analyzed its mass through series of experiment, it was come to a conclusion that alpha is nothing but, or it is very similar to a helium nucleus. Okay, so what does a helium nucleus possess? 2 protons and 2 neutrons. So alpha is similar to a helium's nucleus, which is 2 proton and 2 neutron. So this has 2 proton plus 2 neutron, and beta is very similar to an electron. All right. So what would be the charge of a beta particle? Just -1. All right. So the mass of an electron will be equal to mass of beta. Mass of an alpha will be the mass of 2 protons and 2 neutrons. If you're a chemistry student, you would know the ratio between the mass of an electron and neutron, like almost 1826, I think so, times an electron's mass will be equal to proton or neutron. So you can get an estimate. So it's almost like 8,000 times heavier than a beta particle. All right. So amongst the three, so alpha is the heaviest, as we have seen now, and beta is not as heavy as alpha, and gamma does not possess any mass at all, right? So, so mass-wise and charge-wise, alpha is the maximum, or alpha possesses the maximum. Beta less than that, and gamma even lesser. I hope that you have understood that. Excuse me. Now here, this term, what does range represent? It represents that, as I said, see, from the nucleus it is coming out. Now these radiations do not travel forever, or they don't carry this energy forever. They give it to the molecules close by, or with which it is interacting, and they lose the energy and become into a totally different particle. What happens in the end, we'll see. So there is a particular range for these particles or radiation that travel through. So what this term represents, how far they are going to travel in a medium. Alright, so range is how far these particles will travel in a medium, is what it represents. Now there are like fixed value in air, how far it will travel. I'll just give you an overview. Alpha travels only 5 centimeters in air, 5 to 7 centimeters you can say. Now beta will travel almost up to 30 centimeters. Gamma will travel a few kilometers. So there is a difference in their range also. Now why is it so? If you think of it, or if you could analyze it, alpha, now that has to be linked with ionization as well. So if you understand ionization, you will understand why the range of these 3 particles are different. All right. Now what is ionization? Again, chemistry students might be quite familiar with. For the others, I'll just tell you, ionization is nothing but like in static electricity we have learnt in physics. It's similar to that. Just removal or addition of electrons from an atom. So when you remove or add electrons, what will happen to the atom? It will become a positively charged ion or negatively charged ion. So this process is called ionization. Alright, so kicking off electrons or making the atoms absorb electrons, that process is called ionization. So if you're in static electricity, what happens? The frictional force removes electron. But here in this case, since we said these 2 are charged particles, and this alpha also possesses more energy, these 3 particles, or these 3 radioactive radiations will have possess the energy to knock off electrons, right? So the ionization ability of these 3 also indirectly influence how far it's going to travel. We'll see that. I'll explain what I mean by it. Before that, how do we represent these? Since this has got 2 protons and 2 neutrons, the charge, we write it here at the bottom, which in other words, the atomic number is written here. The mass number is written there above. And for beta, what is the charge? It's -1, and it does not have any proton or neutron, so it has got 0 there, mass number. For gamma, you don't have to write anything because it doesn't possess any charge. So this is the representation here. So this 2 represents the number of charged particles, which in other words is the atomic number. This 4 represents the total particles inside the nucleus, which is in other words the mass number. Okay, I hope you got that. Now since it has got 2 protons, it's easy for it to absorb these electrons in its path, right? Because it is, as we said, heavier, it will interact with more molecules when it is passing through the air, and also it has the ability to knock off electrons from, because it has got the attractive power, it can do that very easily. So it will quickly lose the energy that it possesses. That's a reason it will not travel further. So it will just travel 5 centimeters. Within that, it will make that many ionization and it stops there. Since beta it has got only 1 electron, it has got it doesn't ionize as much as alpha, so it can travel further because it still possesses that energy. How about gamma? It will cause the least ionization because it can pass through almost all material, hence it will travel, it will not interact with molecules at all, so it is going to travel longer distance compared to these. Alright, so why does alpha stop? I hope you would have reactor, it interacts with more molecules and the ionizing power is greater, so it loses energy quickly. Excuse me. Beta will travel further. So this is around 5 centimeters. This is around 30 centimeters. This is going to be in kilometers. All right. That's about ionization. Mass also we have compared. Now, what is GM counter and background radiation basically? Now, the radiations, the number of radiation, because when you're comparing isotopes and we are going to discuss about the effects of these radiations, whether it's going to be harmful or whether we can put it into useful form, etc. For that, you need to know how strong these radiations are, or the isotope, a particular isotope, how strong it is going to be. It will depend upon how many radiations it's giving out in a second. Isn't it? We need to have that for us to compare these strength of these radioactive isotopes. For that, the count, the number of radioactive radiations given out in 1 second, that's actually called as, if I say 50 radiations are given out in 1 second, we term it as 50 becquerels. In short, you can write it as BQ, named after the scientist who invented. So 50 becquerels, the number of 50 radiations will be emitted in 1 second. If you say 100 becquerels for any other element, which means it emits 100 radiations in 1 second. All right. Now, how do we record this? How do we know these radiations? Because we can't see. It's like all these electromagnetic, infrared, ultraviolet, it's invisible to us. So you have learned this in electromagnetic radiation, those 7 electromagnetic rays that you have learnt. This is the last one, right? So you can't see it at all. So you can only see its effect. Hence, we use a GM counter, okay, to record these radiations, and you will come to know how many radiations are there. Now, for IGCSE, you don't need to know how a GM counter is constructed, but I'll put it as a separate video. If anyone is interested to know it, you can know it. But for examination point of view, you need not know about how a GM counter is constructed and how it works. But you need to know for what it is used in radioactivity. It is used to record the number of radiations that is emitted by an isotope. All right. Now, what is this BG radiation? It stands for background radiation. What does that mean? See, the sources of isotopes, right? Naturally occurring isotopes, you may have it on the surface of the earth from the volcanoes. It is erupted. So that is one source of isotope. Another, radiations. Another source of these radiations would be from cosmic rays, from outer space it would have entered, or the human intervention. Now we are conducting like nuclear power stations or other experiments are held in different parts of the world. So from there also these radiations might be given out in the atmosphere. So if you record with a GM counter without any even radioactive isotope present around in that area, you will still see that it records some radiation. The amount of radiation present in the atmosphere is background radiation. All right. So how will you define it? The radiations present in the atmosphere will be contributing to the background radiation. The sources, the main sources, as I said, are the naturally occurring radioactive isotopes on the surface of the earth, or the cosmic rays coming from outer space, or due to human intervention. All right. I hope you would have understood what each term stands for, and you would be in a better position to write it clearly using your own words and using the proper key terms. All right. See you in another video. Bye.